At the heart of measure theory lies a simple but powerful idea: measuring the size of sets. Think of a set, call it omega, as the universe we care about. We'd love to assign a meaningful notion of size to all of its subsets. But here's the catch. It turns out that it's actually impossible to do this for every subset without running into contradictions. So what do mathematicians do? Instead of trying to measure everything, we restrict ourselves to just the well-behaved subsets, the ones we can measure consistently. And the collection of these nice, measurable subsets is what we call a sigma algebra. In other words, a sigma algebra is the carefully chosen playground where measure theory works smoothly. In measure theory, we're after one central goal: assigning a consistent notion of size to subsets of a set omega. But here's the problem. Not every subset can be measured in a way that works with the axioms of a measure. Some sets are just too wild. So instead, we focus on the collection of subsets where measurement actually makes sense. That collection is called a sigma algebra. Now, what makes a collection of subsets a sigma algebra? Mathematicians boiled it down to three simple but powerful conditions. First, the collection must include the empty set. Even nothing should be measurable. Second, the collection must be closed under complements. That means, if a set A is measurable, then everything outside of A, its complement, omega A, must also be measurable. We don't want measurability to break when we flip our perspective. Third, the collection must be closed under countable unions. If you take A1, A2, A3, and so on, infinitely many measurable sets, and unite them, their union must also lie in the collection. In other words, measurability survives when we build larger sets from countably many smaller ones. These three conditions together give us the precise definition of a sigma algebra. It's the framework that guarantees consistency, and it's the stage on which measure theory can actually work. To get a feel for this definition, let's look at the two simplest sigma algebras you can possibly have. Think of them as the two extremes. On one end, we have the trivial sigma algebra, just the empty set and the whole space omega, nothing in between. It satisfies all the rules. It has empty set, it has omega, and complements, just swap them back and forth. This is the smallest sigma algebra you can imagine. On the other end, we have the power set sigma algebra, the collection of every possible subset of omega. Since it contains literally everything, it's automatically closed under complements and unions. This is the largest sigma algebra you can have. And here's the key point. Every sigma algebra you'll ever see lives somewhere between these two extremes, bigger than the trivial one, but smaller than the power set. We just saw the three rules that make a sigma algebra. Now let's see what those rules immediately give us and why they're so powerful. First, if the empty set is measurable, then so is the whole universe. That's because complementation flips nothing into everything, and measurability must hold both ways. So the full set omega is always in the sigma algebra. Second, closure under countable unions automatically gives us closure under finite unions. If we can glue together infinitely many sets, we can certainly glue together 2, 3, or 10. And finite unions are the bread and butter of everyday set manipulation. Third, once we combine complements with unions, we also get intersections, even countable intersections. That's just De Morgan's law in action. So whenever A and B are measurable, their overlap is measurable too. Fourth, differences are safe as well. The set A minus B is just A intersected with the complement of B. Since both intersections and complements stay measurable, differences stay measurable too. Altogether, this shows a sigma algebra is a very stable environment. Once a set is measurable, almost every natural set operation you'd want to do keeps you inside the measurable world. Now, let's talk about structure. One key idea is that of an atom. An atom is a minimal measurable piece, a set so small that the only measurable subsets of it are itself and the empty set. You can think of atoms like indivisible building blocks. If you partition omega into atoms, then the sigma algebra made from them is simply every possible union of whole atoms. In other words, if your universe is split into labeled boxes, the measurable sets are just all the ways you can combine those boxes. Next comes a practical question. What if we don't already have a sigma algebra, but we do have some starting collection of sets called B? How do we get a sigma algebra that contains them? The answer is simple but deep. We take the intersection of all sigma algebras that already contain B. That intersection is itself a sigma algebra. It contains B, and it is the smallest one with that property. We call it the sigma algebra generated by B, and we write it as sigma of B. In these notes, why is this important? Because in practice, we almost never start with a full sigma algebra. We start with natural building blocks like open intervals on the real line, or the cells of a partition, or the preimages of a function, and then we let sigma of B be the minimal measurable world built from those pieces. The most famous case is the Borel sigma algebra on the real line. Start with open intervals, close under complements and countable unions, and you get a massive collection of measurable sets. That's the standard sigma algebra for real analysis and probability. So let's recap. The three defining rules automatically give us closure under unions, intersections, and differences. Atoms give us a way to picture minimal measurable building blocks. And the sigma algebra generated by a family of sets is how we enlarge a small collection into a full, consistent, measurable universe. These tools together form the foundation where measure theory actually works.